did last lesson. Okay, we summarize what we did last lesson first. Okay, then we can start on our tutorial questions. Okay, so anyways, last lesson, right? I'm more going to focus on the later half parts. Like the earlier half, like earlier first 7 pages are like a bit redundant. Okay, but we talked about primary, secondary, and tertiary halogenal alkenes. Remember that there will be 2 different types of reactions, SN1 and SN2, that has many features. I'll go through those features again. But first of all, we must understand under halogenal alkenes, the main reaction is nucleosub. Okay, nucleophilic substitution, the main reaction that we're going to look at for this topic. But before we looked at the mechanism, we went through 3 different reactions. These 3 different nucleophiles are used to react with halogenal alkanes. Okay, the first one is your OH minus. Okay, so very simply, you can turn a halogen into an alcohol. Okay, just via a very simple substitution reaction. Reagents and conditions, you all can refer to the notes. I'm not going to go over that. Okay, and the second one was on nitriles. Nitrile, same thing. You can take a halogenal alkane, substitute it into a nitrile. But before we move on to our third reaction, right? Nitriles actually got further reactions. Again, you will never see nitrile as a topic, a standalone topic in your syllabus. So for nitriles, right, we deviate a bit. Okay, we have a few reactions with nitriles. Okay, again, let's just go through this one more time. Okay, 3 very important reactions. The first one is called acidic hydrolysis. Okay, so acidic hydrolysis, remember, I gave you guys the definition of hydrolysis in organic chem. Okay, hydrolysis involves what reagent? What species? Hydro means water. Okay, so you involve water, you use water to break bonds. Okay, that was the definition of hydrolysis. Right? Okay, we use water to break bonds in organic chemistry. Okay, so for this particular purpose, right, a nitrile can turn into a carboxylic acid. You break the CN dark triple bond to turn it into a CO2H. I'm not going to write out the full valence equation, but what's important also is I'm going to form the NH4 plus. That's where the N has become. Okay, so that's for acidic medium. But of course, if there's an acidic medium, there will definitely be basic medium. Okay, basic hydrolysis. But I want you guys to not just memorize the products, but kind of guess what the products are. Okay, if I get a carboxylic acid in acid conditions, basic conditions, what am I going to get? Remember, what do I get under a basic condition? Do I also get a carboxylic acid? No, right? An acid must react with a base to form a salt. Okay, so I'm going to form a carboxylate salt. Essentially, it's CO2 minus. I have deprotonated the H plus simply because I'm in the basic condition. Another one will be this, guys. Why get NH4 plus? No, this is the conjugate acid of the base, which is Na3. Good. Okay, so again, it really depends on the medium. You don't have to blindly memorize it. You can just understand from the reactions and see that so far. And remember, if you have Na4 plus here, this is Na3, right? Which one will you choose if you want to see a visible observation? Na3. Okay, Na3, you can smell it, right? That's smelly. Okay, NH4 plus, there's no observation, so it's not good for distinguishing test. Okay, can so far? Right, okay, so that's that. There's a third reaction also. Can you remember what that third reaction is? Okay, reduction. Okay, so there's a reduction of nitriles, and basically, I can take a CN, and I told you guys that if you want to reduce something, you just add. Okay, you just add H so that it becomes CH2 and H2. Anytime you see an NH2, this is a B functional group. Okay, carboxylic acid, carboxylate salt, pretty much the same thing. Right, again, then we have AB also. Okay, but more importantly, right, guys, this reaction here from nitrile, okay, you want to substitute a nitrile, is also known as a what kind of reaction? What's a very useful thing that it does? I started off with 2 carbons and then I ended up with 3 carbons. Okay, remember what this is called? Step up reaction. Good. Okay, our only way to step up a compound, to increase the number of carbons, is by using nitrile. Nothing else. No such other thing in your syllabus. Okay, so this is known as a step up reaction. You can note it down somewhere. Okay, just put it here on step up. Okay, that's not the actual name of the reaction. If they ask for the name of reaction, what must you tell me? Nucleosub. Okay, there's no such thing. They ask you, oh, it's a step up reaction. No, no such thing. It's just a name that you we call it, right, we see that the number of carbons increase. Okay, finally, right, there's this one very confusing reaction. Okay, there's NH3. Okay, so I can just take a halogen and then I can substitute directly into amine as well. What's the difference though? Here I can form an amine, but why, there's another way to form an amine here. What's the difference between these? How come there are two ways to form amines? Can you all see that this one, right, is after you added a nitrile. You turn it into a nitrile first, then you become an amine. If you want to increase the number of carbons, you opt for this instead. If you don't want to increase the number of carbons, you opt for this now. Directly, you can just substitute, right? Okay, but I want to go through the four reactions because a very special feature of this guy is that it can undergo multi-substitution. Okay, I went through this in class the other time, but you may not be able to follow. Okay, because online lesson and all that. Okay, but remember, there are some principles behind this. How come multi-sub can occur, so on and so forth? Okay, let's start with the easiest, bromine. Okay, bromo-ethane over here. Okay, so if I substitute with an NH3, it's not very, very straightforward. I'm just gonna get a NH2 amine plus HR. Now, first question, what kind of amine is this? Primary, secondary, or tertiary? Okay, just like one alkyl group bonded to the end, right? Okay, so this is a primary amine. Okay, let's just keep it at that. But guys, why this reaction can continue substituting? Remember, there was a criteria for multi-substitution. As long as there is white, then the multi-substitution can occur. Good. As long as you have a nucleophile, right? It's a nucleophilic sub. What makes something a nucleophile? As long as the nitrogen here has a lone pair. As you can see, the ammonia has a lone pair, that's how you can undergo substitution. But it doesn't stop here because the amine also has a lone pair of nitrogen. So remember, as long as there is lone pair of electrons or nitrogen, you can undergo multi-sub. I'm not looking at the H and the Br. It doesn't matter whether there's H or Br. We talked about that last lesson, so you can remember that, right? It's not about H and Br. It's just a byproduct, okay, but it's more on the lone pair. Okay, so let's look at the other products as well. Okay, I got the same, it can react with the same halogen alkane because as long as there's a ridge, this guy must be one. If this guy's ridge, this one definitely poor. Why is which part of this guy is poor? Is the carbon that's bonded to the Br that's poor, right? That's why this lone pair can attack this carbon here. That's why you end up seeing the nitrogen attached to that carbon. See that? Okay, so we're going to do the same thing here again, right? You can definitely see that this amine, the primary amine, can undergo the same reaction simply because it has a lone pair. The lone pair attacks this carbon here. I know you can draw partial charges, but let's not waste time with that. And then the end, right, is going to bond to another two more carbons. Can you see that? Okay, these two on the left are existing, but then now you have more on the right. From two H's, you drop to one H because one H comes out to form with H. Yeah, you can see that so far. Okay, so this is a what kind of amine? Secondary amine. You all can think of it this way. Later we'll try one question related to this. Okay, this is I have one wing, now I suddenly have two wings. Okay, like bird like that, right? Like this guy. Okay, so now, right, okay, we can continue reacting because the nitrogen still has a lone pair. Okay, so I'm just going to take out my bromine one more time. Okay, just going to take out my secondary amine, and then it's still going to undergo one more round of reaction. Okay, I'm going to draw this painstakingly one by one because I need you all to recognize how the product develops. Okay, so now how does it look like? How many wings does it have? 3 long. You see, the wings are always goes according to the number of carbons the halogen alkane has. 2 carbon, very easy. What if it becomes 4 carbons? That would be very, very bulky. Okay, that has happened before. Okay, so 1, 2, these are the existing 2 wings, but now you have the 3rd wing down here. Okay, the H comes out to form H. Yeah. Okay, so far. But again, it doesn't stop here because it has a lone pair. Okay, this is tertiary. After tertiary is what? Can I remember? After tertiary, we have 4 is called quaternary. Okay, it's primary, secondary, tertiary, quaternary, but it's no longer amine. Okay, we will see why. But same thing, you still have the end attacking this carbon. You can gain a 4th wing. Let's see that. Okay, but at this point, right, the nitrogen form 4 bonds. Not really. Okay, but then it's just it can do that, but then it must have a positive charge. 1, 2, 3, 4. The nitrogen now has a plus charge, and then you get Br minus instead. So this one is a tricky one because it's plus minus, it's like a salt. So they call it a quaternary ammonium salt. And guys, does it continue? Why not? Yeah, okay, there's a plus charge. Plus charge means you're poor, so you confirm definitely do not have a low tank. So that's where we stop. Okay, but there's a pattern I'm going to prepare you guys for the question we're going to do later. Okay, we have 2 carbons. How many carbons we have here? Okay, 2 carbons followed by, and finally, 2, 4, 6, 8. There's an increment of 2 because, why 2? The original halogenal alkane is 2 carbons. If the original halogenal alkane is 4 carbons, then it's 4 carbons here, right? 4, then 8, and so guys, yes, you can possibly get for 4, you started with small little 4 carbon, it can spiral out or through until 16 carbons. Definitely possible. Okay, there will be questions testing you on this. Okay, can very, very slightly complicated reaction, but I hope you all can have a better idea now. Any questions? They all clarify. Okay, no. Okay, one final thing is this. You can have multi-sub 1, 2, 3, 4, or you can have mono-sub. Just do the first one. How do you simulate that? Guys, multi-substitution. What is the condition that you need to add? Okay, we go through this again. Right here. Okay, so multi-sub, what is one reagent that is present in all 4 steps? What is that common ingredient that must be a lot so that it can be present in all, it can happen in all 4 steps? Halogenal alkane. Can you see I purposely write them all on the left hand side? Because if you want this to carry on a lot, a multi-sub happen all 4 times, then you just make sure you put a lot of that guy. You put excess halogenal alkane. Finish. So conversely, guys, if you want it to be a bit only, then what do you do? 1 substitution, enough. What should you do instead? You limit this guy instead. But unfortunately, right, we see ammonia being used as well, right? So that's why if there's excess halogenal alkane, that means your ammonia must be what? Limited. And this is where things get a little bit counterintuitive. A lot of people think multi-sub means you add a lot of ammonia. That's wrong. Okay, it's actually limited. And conversely, mono-sub is actually excess ammonia. Okay, it is the opposite. So the best way to look at it is actually via the halogenal alkane. Okay, so far. So important revision here, okay, this is what we did last lesson. Okay, but then beyond this, right, the second lesson that we went through, we talked about mechanisms. Now I need to go through one more time, okay, before we look at it forward. Okay, any questions so far? Okay, all good. Okay, when it comes to SN1 versus SN2 nucleosub, okay, there are a bunch of features that we can just look through very quickly. Okay, let's look at SN2 first. Okay, there are a bunch of features that we can list out. Remember, absolute number 1 thing. The 2 is what? SN2. What is the 2? Is it 2 steps? Okay, good. Okay, must remember that. Okay, 2 reactants in the what? In the entire mechanism. 2 reactants in the slow step. Okay, must be the slow step. Okay, that's why there is kinetics involved. The rate equation is K times halogenal alkane times, what's the other thing? Okay, what's the other reactant also involved? The nucleophile. NU stands for nucleophile. So nucleophile here will affect the rate. Later there will be one question regarding this. Okay, we will see. Okay, so how many steps are there for SN2? Okay, it's just a 1-step reaction. Okay, remember, why is there a 1-step reaction? What do you form in between? What's that thing called? Okay, what's that thing called that you form in the middle of a SN2 reaction? Transition state. Is that thing real? No, okay, it's not real. Transition states are not real. That's why it's still considered a 1 whole step. Okay, transition state. Okay, many other features we're going to look at. Okay, other than that, okay, there's a lot more in the notes. Okay, there's another one. How is the nucleophile attacking the carbon? Just anyhow attack? Okay, how does it attack? It's a very specific direction. It attacks from the back. Yes, again, it must attack from the back. It likes to surprise. Right, okay, so you must have a real side attack. And guys, when you attack from the back, this will cause something to happen. What will happen to the stereochemistry? Remember? it will invert. Okay, the inversion is just when you draw the mechanism that time I tell you guys all the details already. Okay, but yes, it will invert the stereochemistry. Okay, just flip to the other side. Okay, I'll teach you guys how to draw it. Right? Okay, so there's that. Okay, there's also other things. Number one, SN2 is preferred by primary or tertiary halogenal alkanes. Okay, primary. Okay, and I say favored by primary. It's not exclusive to primary, because it is possible for tertiary to undergo. Just a much lower chance. Okay, I asked you guys to write it down the big piece of paper, also that table, right? Okay, we can go through that very briefly later on, right? But guys, why does primary halogenal alkane favor SN? Remember telling you guys for SN2, what's the factor you need to argue? Okay, you can just refer. For SN2, you must argue in terms of what factor? Steric hindrance. Okay, so we went through that in the table last lesson. Okay, steric hindrance. Guys, primary halogenal alkane. Is there a lot of steric hindrance or very little steric hindrance? Little bit, right? Because why? Primary has very little bulky alkyl groups. Right? Okay, the less the better one. Then the nucleophile can just attack from the back. Right? Okay, so it's the same idea here. Okay, you have low steric hindrance for a primary halogenal alkane. And that's why primary tends to favor SN2. Guys, can I say that, primary, or can I say primary undergoes SN2 because it doesn't undergo SN1? No, am I answering the question? Okay, some of you guys are, what the hell? Right, okay, so that's something we need to avoid. Okay, if they ask you, why do you favor SN2? You don't tell me that, it's because I don't favor SN1. You're not answering the question. Or conversely, guys, why do I not like SN2? It's because I like SN1 instead. Does that make any sense? Okay, again, don't change the subject. If the question says SN2, you talk about steric hindrance. You talk about SN2 only. Okay, that's what we highlighted last lesson also. Yeah, I use the example, right? Okay, why do you not like coffee? Because I like tea instead. No, it doesn't make sense. Okay, I don't like coffee because it sucks. Okay, that's the idea. Right? Okay, it just tastes bad. Okay, so that's the idea here for SN2. Okay, we're going to continue that with SN1. Okay, guys, so we do the same thing. 1 means what? The big fat 1 over there means what? Okay, good. 1 reactant in the slow step. Good. And having 1 reactant means, okay, your rate equation is just the what? Is it the nucleophile or is it the halogenal alkane? Okay, the halogenal alkane. In other words, guys, in SN1 reactions, no matter how much nucleophile you add, it's not going to make it faster. You see that? Doesn't affect. Okay, how many steps are there? Then conversely, there will be 2 steps, guys. Why are there 2 steps? Because what do you form in the middle? The real thing. Okay, just now the fake thing is called a transition state. The real one is called a carbocation, which is also known as your intermediate. Okay, it just happens that here the intermediate is a carbocation. Okay, next, what's the special feature when it comes to stereochemistry for SN1? Okay, you all take a look at the carbocation, the carbon with the positive charge, right, has what shape? Carbocation, just 1, 2, 3 with a plus charge. What shape is this? Yes, and guys, if the carbocation trigonal planar, what does that do? What will the nucleophile do? It can attack from, imagine it's completely flat, planar. So the nucleophile can attack from the top or the bottom. What are the chances of doing so? The same. And then you end up with what? A what mixture? Racemic mixture. Okay, so remember, the entire explanation leads to that. Carbocation is trigonal planar, leading to a racemic mixture. So you must look at the different stereochemical special property. SN2 will form chiral compounds. It's just that, it's just split. This one right here is just racemic mixture, 2 equal proportions. Okay, so that's the stereochemistry. Okay, next, it's favored by what? Tertiary halogenal alkanes. Good. What is the argument that I use to argue SN1? What we talk about instead? SN2 we talk about steric hindrance. Okay, the stability of carbocation. Okay, dispersing the positive charge. The more dispersed the positive charge is, the more stable the carbocation is. Okay, so why tertiary is just very stable? Tertiary halogen alkanes have more what compared to primary. Yeah, the fact is it has more alkyl groups, and alkyl groups are what? They are described to be electron donating. The more electron donating alkyl groups you have, the less poor you are, right? So that's why you can see the explanation that I've given you guys. Okay, positive charge dispersed to a greater extent, and that's more stable. Okay, so we talk about more stable carbocation intermediate. Again, they ask you why does it not favor SN1? It's because the carbocation is stable or not stable? Not stable. Don't go and tell me about stability because don't even bother about it. Okay, so that's SN2 and SN1. Okay, we talked a little bit about halogenoarenes as well. Okay, but that way you can just use the notes to, we can use the questions to recap. Okay, we talk about how, okay, just very quickly, if we have a halogenoalkane that is attached, a halogen directly attached onto a benzene, and that guy undergoes substitution. Can you cut this bond out and then substitute it with something else? Okay, answer is no. Remember that anything that is stuck directly onto benzene cannot undergo nucleosub. Why, guys? If you can't undergo nucleosub, that means this bond can break or cannot break. Cannot break. Cannot break implies the bond is very strong. Why is the bond very strong? What was the reasoning behind this? The bond here has partial double bond character. Okay, this has to do with a little bit of your delocalization theory. Okay, we talked about that when we talked about halogenoarenes. Okay, this is the main reason why it doesn't undergo nucleophilic substitution. But it can undergo electrophilic substitution because there's a freaking benzene ring on it. Okay, so it's still normal. That's just a few weeks topic. Okay, that's pretty much all we went through. Okay, we also went through something about distinguishing tests. Okay, but we covered that last lesson already. Any questions so far? Okay, so that's an overview of the topic. The first part was all these three reactions here and nitrile. Second part is mechanism. Okay, so this is where we're gonna look at the tutorial questions. And so far, okay, quick recap. Okay, so take out the tutorial, right? Last lesson we did a few questions here and there. I want you guys to now turn over. Okay, let's start off with something okay lah. Okay, we start off with a warm-up question first. Can you all turn over to question 3? Yeah, okay, turn over to question 3. So I want you all to look at part A. They ask you to write the reagents and conditions. Okay, I suggest draw out the structure also lah. Okay, and then afterwards I want you all to try part 1, where you need to draw the mechanism. Okay, so question 3, A and part 1. Again, try to draw skeletal. No? Let's draw a structure first. Right. Reagents and conditions might need to refer to the notes. Okay, one thing is this, you see C4H10O, right? This is a molecular formula. We have no idea how it is arranged, but we can infer what it is, basically. Okay, so I saw the structure is a little bit funky. Do you all realize, right? This is a halogenal alkane. Then you notice the molecular formula. The halogen is gone, but it's replaced with a O. Which one of the three nucleosubs, right, did we learn? Okay, so that was the reaction, right? Okay, you just have to choose which nucleophile was used. Yeah, so what do you guess what this first structure is? Structure C. Okay, it was a halogenal alkane, and then this one has to be an alcohol because it can undergo nucleophilic sub. And out of the three, okay, out of the three nucleophiles we went through just now, only one of them can have an O, which is your alcohol. So that's it. That's your first structure. Okay, once you've identified the structure, then we can write down the reagents and conditions. Okay, so can you remember what are the reagents and conditions for this? Okay, so that it was in the notes also. Okay, but then this one, right, if you want OH minus as a nucleophile, so definitely you have NaOH, the aqueous state, and also you must heat. Why do you heat? Because you are trying to do what? Break the CPR bond. Definitely need to heat that. Okay, now on the other hand, guys, can you all recognize what C4H is? Sorry? Alkene, good. Because an alkene has a general formula of C4H8. Now you notice something. Okay, the Br is gone. And then you have C4H8 and alkene. What reaction is this? The first one was nucleophilic sub. The second one, is it nucleophilic sub? If you form back an alkene, this is a what reaction? It's an elimination reaction. Okay, so there are some possible double bonds that you can form over here. Okay, elimination reaction, take a look at the reagents and conditions. Okay, if you refer to your notes, it says that ethanolic NaOH. And then now, guys, do you realize that the reagents and conditions are very similar? They are very similar. The only difference is the what? Yes, the aqueous versus ethanolic, you can see that. Okay, aqueous state means the solvent is water. And if you use a water solvent, you're going to have a neutral substitution. On the other hand, if you use ethanolic, ethanol as a solvent, you're going to push for the elimination reaction to happen instead. Okay, so that's your answer for part A. Now, they never ask you to draw the structures out, okay, but then of course you can kind of guess the structure for part A. The structure for the elimination, right, this guy here will be done later on. Okay, so this is one of the parts. Okay, as of right now, okay, take a look at part B. B part 1, they already tell you what the mechanism is. Now, guys, they told you guys it's SN1 mechanism. Now, if you take a look at this, okay, would you have guessed that this was SN1? How do you check if this guy is favoring SN1 or SN2? Primary versus tertiary, right? But this guy is what? Secondary. Okay, remember, secondary undergoes what? It undergoes a mixture of SN1 and SN2. Okay, we do not know for sure. That one must look at the question to tell you. So now the question tells you there's SN1 mechanism, right? Okay, so try to draw the SN1 mechanism. Okay, so just remember to draw in your title first, SN1 nucleophilic sub, must specify SN1. Okay, then from there, right there you try. SN1 only have one reactor in the slow step one. So looks like you've found the mechanism. Okay, so let's take a look. Remember, SN1 is a two-step mechanism. Okay, for the first step, okay, I just want to see the halogenal alkane undergoing a reaction. No nucleophile. So remember how it looks like for the first step. The carbon has a partial positive, the halogen has partial negative, and this bond just straight away breaks and goes towards the phenol. This just happens on its own without any provocation. Okay, so slow step. Then the carbon here must have a one charge. The carbon that just broke apart is bond. It just lost something, right? So now it has a plus charge. On the other hand, bromine has just gained an electron. So he must have a minus charge. So now I've formed the carbocation. You now take the carbocation and react it with what? Now then the nucleophile comes in, which is your OH minus. Remember, I need to see the lone pair of O, because electron movement. From there, you must attack the carbon with the positive charge. Do not attack the positive charge. You see that? Okay, then from there, SN1 reaction usually very easy to draw compared to SN2. Okay, so this is the answer. Any issues? Okay, this is easier. Okay, then we take a look at part 2. Part 2, they ask us to explain quite a few things. Okay, so this one you can go give it a try also. Right? Okay, try, there's like 3 parts in part 2. Okay, you can go and explain that. Okay, very conceptual question, just to reinforce a few things. Okay. Which part you want to know? Okay, yeah. You know how to explain the term racing mixture, is it? Okay, what is a racing mixture? Based on your own understanding. Okay, yeah, not wrong, not wrong. Okay, but what's so special about racing? Any idea? Okay, how do you form a racing mixture? The nucleophile attacks from the top and bottom. What are the chances of this happening? Equal. Okay, if you attack the top, you get a structure that attacks from the top. You attack from the bottom, you get a structure that is attacked from the bottom. Two different structures, two different enantiomers. What's the proportion of both of these enantiomers? Also equal, right? Because the chances of attacking the top and the bottom is also equal. So now that you have equal proportions of both enantiomers, that is called a racemic mixture. So a racemic mixture is just containing equal proportions of two enantiomers. That's pretty much it. Okay, a normal image and a mirror image. Both of these guys are equal proportion in the same mixture. That's pretty much it. Okay. Two equal proportions of two enantiomers in the same mixture. You want to add in that word also can. Okay, but the drawing part, okay, so of course, you all take a look at this guy here. This is my chiral center. I'm sure you all can see that, right? From there, you just need to convert it into your solid bonds and your wedge bonds. Okay, so I'm going to make this. Usually, the solid and wedge bonds look like this. I want to make the smallest atoms on that chiral center, the solid and wedge bonds. So what I'm going to do is this. Okay, you all look at this structure here. Okay, I'm going to do something like that. My OH now has a solid bond. Can see that? The H can be invisible, but let me just draw it out, okay, as your dash bond. That's pretty much it. You don't need even to convert, you don't even need to convert it to a structural formula. Okay, but if you want to, go ahead. Okay, then you draw the mirror, and then afterwards you just need to mirror that thing. Okay, I still have my OH pointing outwards, my H pointing inwards. This right here are your enantiomers. Okay, drawing of enantiomers is part of it. Okay, then of course we have the second and third bullet point. Okay, all those we just need to fill in the blanks here. Okay, we can fill in the blanks together. All good? Okay, let's go through the blanks together. To explain the second one, how does a racemic mixture form? Okay, guys, what are the keywords here? First of all, you must tell me the carbocation is what? The carbocation has a specific shape that allows for this to happen. What is it? Yes, okay. You must first tell me the carbocation is trigonoplanar in shape. That's why allowing the OH minus nucleophile to attack it from both sides of the plane with what? Equal probability. Yes. And that's why you form a racemic mixture. It's the same template answer we've been doing since alkenes. Okay, over. Okay, as for part 3, okay, explain why product C is optically active even though it has a chiral center. So guys, you see the first two parts have pretty much just built up together. Okay, there is a normal image and a mirror image. Yes, both of them can rotate plane polarized light, right? Okay, but somehow it doesn't rotate plane polarized light. Why? It's because what's so special about a racemic mixture? A racemic mixture means you have equal proportions of both normal and mirror image in the same mixture. So what does that mean? Remember, how does a normal image rotate plane polarized light? Okay, they rotate plane polarized light by the same extent, right? Okay, now you do not need to know what plane polarized light is. Just think of it this way. Enantiomers have a very special power that nothing else has. It can somehow rotate this thing called plane polarized light. You don't take physics, right? Yeah, okay, so don't need to know what plane polarized light is. No need at all. It's a very physics concept. Even I also don't barely understand what it is. Yeah, okay, but basically light is split into multiple waves. Then you can like, okay, it's very complicated. I tell you, you also do one. Okay, but the point is light can be rotated somehow using enantiomers. It's a special power. Okay, so guys, think about it. This normal image can rotate plane polarized light by 15 degrees. That means this guy will rotate by how many degrees? Also 15 because same extent, right? But because it's a mirror image, it's what 15 degrees? Negative 15. It's actually in the opposite direction. So take note, okay, this is the relationship between the enantiomers. They rotate by the same magnitude, but opposite directions. Meaning, guys, if both of them are equal, because we say already, they're both equal proportions in the same mixture, right? What's the overall rotation? Equal proportions. 1:1. So overall, you put them together, what's their direction of rotation? One rotate plus 15, the other rotate minus 15. You put them together, they rotate by 0. It cancels each other out, can see that. That's why there is no net rotation of plane polarized light. That's why it's optically inactive. Can see that? Okay, guys, let me just give you another scenario. This is equal 50-50, right? We will only be dealing with 50-50. But guys, imagine this, I got 70% of this, 30% of this. Can you tell me, overall you rotate in the positive or negative direction? Positive, right? Okay, it's weightage. This has a greater significance. You see that, right? Okay, it's just that when they're equal, they will cancel each other out. Okay, any issues so far? So this question here, okay, very, very conceptual. Anything else? Okay, can okay, we're slowly gonna ramp up, okay, the difficulty also. Okay, I remember last lesson we did question 4, but we didn't do the whole of question 4. Yeah, we didn't do the whole of question 4 if I'm not wrong. Okay, we will try to finish this up first, the rest of question 4. I can't remember which one we did already. You can someone help me check. I remember we do A to C. A, C, and E. Oh, we did A, B, C, and E. Okay, that's a lot. Okay, we try D and F, no? Right, okay, can you take a look at D and F? Yeah. Okay, do D first. Okay, try to draw the skeletal structures of the start and the ending compound first. Right? Remember what I told you guys the last lesson of this kind of reaction synthesis questions, you must always count the number of carbon atoms first. Okay, count the number of carbon atoms, sometimes that can give you a clue. Right? Okay, so after you counted the number of carbons, what do you all realize? Anything you all realize? Okay, what do you realize here? Okay, there's more carbon, so this is a what reaction? Okay, it is a step-up reaction. Now guys, when it comes to step-up reactions, what is the reaction that we have learned that allows us to step up the number of carbons? Okay, nitrile. Turning a halogenoalkane into a nitrile is the only way to step up carbons, right? So that means this reaction here must happen somewhere in this process. Okay, we have streamlined our idea to just this. So guys, I somehow need to take a halogenoalkane and turn it into a nitrile. Do I have a halogenoalkane at my disposal right now? Yes, I do. It's right here. So why not you just immediately turn it into a nitrile? Okay, but there's both halogens, right? So what should I do? Should I just turn one only? No lah. You can kind of see the product as well. Both sides right, end up having the same thing. So you want to react both sides also. It's such that here you have nitrile on one side and nitrile on the other side. So just because there are two halogens, right, it allows us to step up twice. Okay, I can increase by 2 carbons. You can see what I'm trying to do here. Okay, so step up must always remind yourself of this reaction happening. You must force this reaction to happen. Okay, and that streamlines, again, it really narrows down our options of okay, to just this. Okay. Any issues here? Okay, let's look at the reagents and conditions. Okay, what are the reagents and conditions here? Okay, this one not really my concern, okay, but then try to start memorizing. Ethanolic NaCN. Okay, if just now I use OH, if I want NaOH, I just add NaOH lah. Here I want CN, so I use NaCN. Okay, followed by P. Okay, how about the other one? What reaction is this? Someone tell me. From CN to CO2H. Good. Acidic hydrolysis, which requires us to use H2SO4 in the aqueous state and heat. Okay, again, this one all just need to memorize reagents and conditions. Yeah. Now, take a look at part F. Part F is going to be slightly tricky, but again, I want to tell you guys count the number of carbons first. I think this one I can go through with you guys together. Okay. Okay, can you count the number of carbons and just tell me what unit is? Step down reaction. Guys, somehow I can go from 4 carbons to 2 carbons. How on earth is that possible? Okay. So, yes, there are step down reactions. And guys, we have only learned, so far, we've only learned one step down reaction. Do you remember what the reaction is? How do I decrease the number of carbons? If I want to decrease the number of carbons, I somehow have to cut the compound. Is there a reaction that allows me to cut the compound? No. Oxidation. Which type of oxidation? Yes, correct. Oxidative cleavage. Remember that? Oh, it's called strong oxidation in alkenes. If you cleave something, it means you want to break the bond. So oxidative cleavage allows us to drop the number of carbons. Okay, so take note of that. Some of you will call it strong oxidation for your school's notes. Okay, but it's also known as oxidative cleavage. Oh no, you haven't seen alkenes. Yeah, it's must start to go and look at it. Yeah, I had alkenes recording lessons on my Google Drive. Please go take a look at it. Yeah, don't watch the school lecture. Use my lecture. Okay. So anyways, yes, oxidative cleavage is to cut the alkenes. Okay, and definitely right. Okay, this is an alkene over here. I can just cut him to get that one, right? Right, do that. No, if you realize something, right? Okay, if I cut like that, right, my products, okay, you cut something, you must have 2 products, right? How big are my 2 products? The one on the left, how many carbons is it? The one on the right, how many? But what I want is what? I want 2. I want my product to have 2 carbons. If I cut it straight away, I'm going to get a product with 3 and 1. How do I cut it such that I get 2 and 2 instead? Can the double bond be there? Then where should the double bond be? In order for it, when I cut already, I get 2 and 2. It should be here instead, right? So now I've narrowed down my scope. Instead of going all the way here, I want it here. I've now narrowed down my pathway from like this to just like this. My job now is to somehow turn the first position into the second position. And if you just take a look, right? Okay, this one, if I undergo the cutting, I cut already, I will get that structure, carboxylic acid. Okay, but now more importantly, is there a way for me to shift the position of an aldehyde? Have we learned directly this happening in one step? Never. Okay, we have never learned a reaction that you can do this in just one step. So we somehow have to do something. What can we do first? Yeah. Okay. Good. I add, then I eliminate. I am repeating that process. Yes, it works. That's the answer. Okay, I add what? Any idea? What should I add? I'm gonna add, then I remove again. Okay, remember, guys, elimination. I highlighted this. It's about what? What are you getting rid of in elimination? You can only get rid of one thing. But for addition, you can add plenty of things. Okay, you can add plenty of things in addition, but for elimination, there's only one thing we are getting rid of. Okay, we are getting rid of HX. Okay, let's take note of that. In elimination, we are only getting rid of HX, nothing else. So guys, if you can only get rid of HX, you take a look at this. They look rather similar to each other, right? You don't want some random halogen to pop out of nowhere. You want things to keep it clean. So guys, what we do here, what should we add so that later on we can remove HX? We also add HX. Can see that? We can't just add X2. If you add X2, right, you remove HX, you have one halogen left behind. Can see that? So I add HX, what's gonna happen is this. I add HBr, I'm gonna get this. And then from here, I eliminate to get this. Can see that? I add HBr here, but I eliminate by taking away the Br here and here. So that my double bond is in the middle now. So it's a slightly tricky question. Okay, it's a challenging question. Okay, but I'm undergoing addition first, adding HBr gas at room temperature. Then I eliminate by undergoing ethanolic NaOH and heat. And then the final reaction is hydroxylative cleavage. So KMnO4, H2SO4, E. So any questions so far? Okay, we're going to try a few MCQ questions right after this because the rest I think we will do already. Right? Okay, all good. Once we're done with this, can you turn over to the level up questions? We're going to do some of the MCQ questions from there. Level up question 1, the ACJC 2018 question. Okay, we're going to try that. I want you guys to read through the question first. And then later we'll discuss this together. Okay, you'll give it a try. Give you maybe 2 minutes. Okay, maybe you can guess and answer. Okay, just do your best. Right, then afterwards, we'll talk about it. Okay, very, very good question. Again, We'll go through this question together. Okay, because this one slightly far-fetched question. Somehow you need to link this into a structure. Okay, so this is what they did. Okay, let me just explain the question first. Number one, they took a halogen alkane to be one of these four guys. They added NaOH and heat. Guys, what does NaOH and heat? Okay, remember, it undergoes a substitution with X, right? So that's why you get an alcohol. But more importantly here, in this question, I'm interested in the X minus, the halide ion. Remember, I liberate this guy first, such that I can react with AgNO3. Does that make sense? That's how I can form my AgX precipitate. What they did, right, is that they are tracking this AgX precipitate. How long it takes to form over time. They are tracking its progress over time. Agree? Okay, so this AgX precipitate comes about, right? Okay, and there are actually two different graphs based on the concentration of NaOH added. Now, guys, I want you to analyze this graph over here. What's the significance? How come there are two different graphs? And what do the graphs even mean? The solid line versus the dotted line. What is the difference between these two graphs? Can someone just tell me that? Look at the shape of the two graphs. Just tell me what's the difference. What do you notice? Okay, good. The which one completes faster? Yes, good. Okay, in other words, guys, you all notice already that the solid line is faster. Why do you all think it's faster? How do you know? Okay, you reach the maximum first, and at the same time, guys, the line is okay, it's a steeper line, so that means the rate of reaction is faster. Okay, so good. Okay, that's something that we notice first. Okay, the rate of the reaction when you use 0.2 mole per dm cube of NaOH is faster because I notice a steeper gradient, or it ends faster. Okay, it's definitely faster than if I use 0.1 mole per dm cube of NaOH. Guys, remember when it comes to our halogenal alkanes, right, we learn of kinetics also. What does this sentence mean here? I use a higher concentration of NaOH, it's faster. I use a lower concentration of NaOH, it's slower. What does this mean about NaOH? What even is NaOH? I think as over here. It is a what? Not just a reactant, it's a what? Okay, what is this reaction here between RX and NaOH? Nucleophilic sum. So NaOH is the what? Is the nucleophile. OH minus is the nucleophile. I use a higher concentration of nucleophile, is faster. I use a lower concentration, is slower. Can you all see that the concentration of the nucleophile affects the rate? Okay. Exactly. Here, the concentration of OH minus nucleophile, if it can affect the rate, that means it is SN1, SN2. Exactly. SN2 reaction is the only one where the rate equation has a nucleophile inside. Can see that? So we are linking all these up together. We are trying to look at rate and how it links to SN1 versus SN2. We talked about the features just now already. This is how they apply the features. Does that make sense? Guys, on the converse, to make you understand this a bit better. If this was an SN1 reaction, okay, I say again, if this was an SN1 reaction, they also use these two concentrations. What would the graph look like? See. Agree? No matter how much you change the concentration, the graph doesn't change. So that's what happens if you use SN1 instead. So in other words, guys, okay, now that we know it's SN2, we somehow need to look at our task. I need to find the help, who the hell to product is. Again, SN2 is usually favored by what? Primary halogenal alkanes. So go and find a primary halogenal alkane. Right? Okay, so take a look at your four options here. Okay, let's just list down our four options. This is what? Okay, is this primary, secondary, or tertiary? Okay, secondary. Now, secondary is there a good answer? Not really, right? If you undergo both SN1 and SN2, okay, never mind. Okay, let's just continue. Okay, how about option B? What's this? Okay, tertiary. Tertiary favors what? Okay, so is that likely your answer? Probably not, okay, but never mind, we do through first. Okay, C, what's this? It's primary. Oh, look, is that answer? You choose C, wrong. Why wrong? Take a look. The chlorine is directly bonded to a double. You don't remember what this means? Yes, you remember. What does it mean when the chlorine is directly bonded to a double bond?
Okay, I found this on the web for what is it? Check it out.
Shut the hell up. It's freaking C. Good. Remember, it doesn't have to be directly bonded to benzene. We went through a question last week as well. If it's directly bonded to a double bond, also cannot. There's partial double bond character. So we're taking note of this. Okay, so there is partial double bond character, meaning can this guy undergo nucleoside? No. Okay, partial double bond character, CCl bond cannot break. So in other words, guys, means what? Will you see a graph that looks like this? What would the graph look like if you try to use compound C instead? Would there be, if the Cl ever come out as Cl minus, would there be a precipitate at the first place? No. So the graph would be zero. Okay, you will have seen no precipitate at all. Okay. Okay, what on earth is D? Is D even a halo if you don't have a? Okay, but what on earth is this? Okay, guys, can you see the Cl? Do you realize the first step here by adding NaOH and heat is for me to get the Cl as Cl minus. In all of these cases, I needed to do that. Except this guy cannot. But see, the Cl minus is already Cl minus. What does this mean about the graph? You see this time taken for it to increase. What is this time that increase? What does this time here represent? It is the time taken to do what? To time taken to, what is it? Okay, you see, why does it take time to form AGX? Okay, yes. It's time taken to break the CCl bond. You all realize this, guys? CCl bond takes time to break. You break it already, and they slowly break, then the AGX precipitate will increase. But guys, is there even a CCl bond to break over here? No. So guys, if you were to use this instead, right, the precipitate will form instantly. Yes, immediately. No need to break CCl bond because there isn't even a CCl bond. Hence, AgCl precipitate will form immediately. Okay, I would say this is one of the toughest questions. Okay. C and D definitely not possible, so answer here would be A. It's the next best answer. I mean, A is not that it cannot undergo SN2, right? Okay, it's just that both SN1 and SN2 is the most likely answer. Answer here is C. Okay, Tama. Okay, I'm surprised it came from ECJC also. Okay, but never mind. The next couple of MCQ not so bad. Okay, can you look at question 2? Later we do question 3 also. These two we do in class before. Okay, take a look at question 2. Okay, give you a few minutes to try. silver nitrate. Okay. That's here. Okay, the silver nitrate. What does it actually do? I remember what we did just now. Oh my god. That would be nasty. Okay, yeah, what does the silver nitrate do? Okay, so do you realize, right? Okay, first of all, this silver nitrate is to form what precipitate? It aims to form a AgX precipitate, the same as the previous question. Yeah, same thing. So then for the first option, they said, right, which one forms precipitate, which one does not? Okay, it's up to you to decide. Right, okay, so which one forms precipitate and which one doesn't? Okay, look at the structures. In the way they place their halogens, it's a little bit different. Look at this answer. Okay, we go through. Is one correct? Okay, so guys, look at the structures here. Can you all tell me which one can undergo, can form the precipitate? Now, first, if you want to form AgX precipitate, first, the halide ion must come out as X minus first, right? So for this to come out as X minus, what must happen to the bond? The bond must break. So it's about whether the bond breaks or not, then you can form AgX precipitate. Can this bond break? Can. Okay, can this bond break? No, because it's attached directly to benzene. So this one can, this one cannot. This one, it's not attached to benzene, so can, this one cannot. That's answer. Okay, so X and C cannot form precipitate, so it's correct, no? How about number 2? Color of the precipitate which forms the fastest is white. Okay, guys, remember this is about rate. Rate of halogen, rate of this nucleosub is dependent on what? Rate here is dependent on bond strength. That's it. Guys, the weaker the bond, be faster or slower. Weaker, definitely faster. Stronger, definitely slower. So guys, they're saying the one that forms the fastest. Okay, out of all the halogens here, who will form the fastest? In fact, you just need to look at Y and Z, because X and Z don't even react. So Y versus Z, we have a CCl bond, Ci bond. Who the faster one has to be weaker. Who's weaker? Yeah. So that means the precipitate here is AgI. Precipitate here is AgCl. So the precipitate that forms the fastest is AgI. Is this guy white? Okay, this one you can check your notes. No. Okay, AgCl is white, AgI is yellow. So the correct answer there should be yellow, not white. Okay? Okay, let's look at option 3. The precipitate which forms the fastest. Okay, who's the guy who forms who forms the fastest again? Okay, then who's the AgI, right? And who's the other precipitate? AgCl. Okay, is AgI does it weigh more than AgCl? Does AgI weigh more than AgCl? Yes, definitely. I is bigger than Cl one, so that's answer one.
You correct.
Yeah, you're right. Oh. Okay, yeah, so answer is B. And we just discredited all work and said you guess one. Oh no. Okay. Yes, yeah, that's good. Yeah, must guess. Okay, can you all just take a look at question 4? Very, very fast MCQ over there. Yeah, okay, they're just asking for the type of reaction, so this one less than a minute. Okay, I can let you all try it. 4. Okay, got the answer here? Okay, let's go through. Okay, so there's usually it's either nuclear sub, nuclear add, electro sub, electro add. Right, okay, let's look at whether it's addition or substitution first. Okay, one thing at a time. Guys, based on your observation here, is this addition or substitution? Clearly, you are subbing this guy with this guy. Must be either answer B or D, substitution. And just look at her like, what the hell? Why judging a banana? Okay, substitution definitely. Okay, but is it nucleophilic substitution or electrophilic substitution? Okay, why you say nucleophilic? Negative, then negative means it's rich, it's a nucleophile, so this is a nucleophile, and the undergo substitution, so it's nucleophile. Okay, that's it. Okay. Any questions? Okay, now we're gonna do the actual like mechanism drawing and all that again. Okay, so let's come back to question 7. Okay, level up question 7. Okay, this is important. Okay, your focus on A part 1. Okay. Now, first thing I want you all to do is to draw out the structure of 1-chloroethyl benzene. Draw this first. Don't do the question yet. Because if you draw this wrongly, your question will be wrong also. So I need to make sure it's correct. Okay, draw 1-chloroethyl benzene. Ethyl is 2 carbons. In a bracket, doesn't really matter. Okay. Remember, when we break down names, I really tell you guys to always read from the right to the left. Right? No, no need. We'll go through. Okay. Yeah, this is benzene. Oh, you guys are. Oh. Okay, ethyl. Ethyl is 2 carbon alkyl group. Remember that, right? Okay, come on, I'll just draw. Okay, so guys, I want you all to break down the name from right to left. First of all, I want you all to look at ethyl benzene. Okay, right to left. What does ethyl benzene look like? Okay, first of all, there's a benzene ring, of course. Okay, you have a benzene. Okay, you have benzene. Ethyl has how many carbons? Okay, 2 carbons. So just put the 2 carbons on the benzene. Okay, start with that first. Okay, then now we look at 1-chlorine. The chlorine is on the first carbon. Read that to yourself. Chlorine is on the first carbon. There's 2 freaking carbons over here. So which one? The issue is what is the first carbon? Is it this or is it this? Who is carbon number 1? Is it this or this? Yes. The one closer to the benzene should be number 1. This is number 1 carbon, this is number 2 carbon. Because remember, you always number the carbons from the end that has the substituent first. So based on these two carbons, you're closer toward number one is bonded to a benzene, so that guy should be number one. Number two is bonded to nothing, so he should be even less priority. Can? So that means the chlorine is on carbon one, so this is one chloroethanol. You see that? That's the answer for this. Okay, and then once you have drawn this out, guys, I want you to draw the mechanism for this guy. They ask you to outline the mechanism and explain how the racemic mixture is produced. Okay? Your job is to decide whether it's SN1 or SN2, correct? But guys, SN1, SN2 preferred by primary or tertiary, right? But this is what? Ah, shit, secondary, meaning the question must tell you something. Guys, what did the question say? Ah, meaning what? Good. Okay, see, these are the clues you went through just now for a reason. Okay, they tell you that a racemic mixture is formed. That's why it must be SN1. Ah, from there, 25. Okay, after that, go explain how the racemic mixture is produced. I need you all to remember the explanation also. Okay. Yeah. Okay, then. Nope, only need to see the title. That's the only name. Okay, the same exact explanation as before. Okay, take note you're using Cn minus here. That's what the question is. Okay, good. Okay, with that said, right, let's go to part 2 together. Okay, for part 2, explain why the following mechanism proceeds via this, which is SN1. In other words, to rephrase this question, they are asking us, right, why does this guy, okay, this dude, favor SN1 mechanism? Why does it favor SN1? How do we argue this? If this compound favors SN1, it implies that this guy has what? Remember, how do you argue SN1 mechanism? Yes. If it is it favors SN1, that means this guy will form a very stable carbocation. Agree? Now, why not? Let's look at its carbocation. It's right here. Okay, take a look at the carbocation. We somehow need to find a reason to explain why this guy is stable. Now, if this carbocation is very stable, it implies its positive charge is what? Okay, the keyword here is dispersed to a. If it's stable means it's dispersed to a very large extent. Good. Okay, it's a stable carbocation. That means this positive charge somehow must be very, very dispersed. Why? Why is it dispersed? Okay, this is where I will teach you guys a new thing here. Whenever you see a positive charge carbon attached directly to a benzene, there's going to be something to do with delocalization. Okay, there will be delocalization involved, okay, to disperse this positive charge. How? Okay, let's look at the specifics. Okay, look at the carbocation over here. Can someone just tell me this carbon with the positive charge is what hybridized? What's its hybridization? Okay, initially, how many bonds does this carbon have? Okay, 4 bonds, okay, visible bond. Then afterwards, you break this bond already, how many bonds does it have? 3. 3 bonds only is what? Okay. Okay, it's sp2 trigonal planar. You can see that. Okay, this carbon over here is sp2 hybridized. And if it's sp2 hybridized, what else? What other orbitals does it have? Okay, good. It has one p orbital. This is quite crucial, because I'm going to draw this diagram again. Okay, I'm looking at this carbon here with the positive charge. Somehow, this guy does actually have a p orbital because he is sp2 hybridized. Previously, does the same carbon previously does it have a p orbital? No, because it's sp3 hybridized. sp3 hybridized, no p orbital. What? Okay, but now that he has a p orbital, what would this p orbital do? Just sit there, is it? He's directly bonded to a benzene, so what will happen? It can overlap with the pi electron cloud of the benzene, right? Remember, a benzene got all 6 carbons have p orbital just overlapping with one another over here. Okay, just all overlapping. It creates a delocalized pi electron cloud in the benzene already, right? But now this guy, is there anything stopping these two from overlapping? No. Okay, it allows this to overlap. And now these 6 carbons plus this 7 carbon over here is all connected. Now, if you want to disperse a plus charge is poor, right? Okay, I want you to take note, delocalization also goes from rich to poor. Who here is the rich order? Is it the carbon with the plus charge? No, right? It is what? Benzene. Benzene there, full of electrons. This guy needs electrons, so where's the delocalization? The pi electrons will delocalize from the benzene ring to the carbon with the plus charge. Basically, you can think of it this way. There's this like very poor guy, right? And then there's like he's like supplementing electrons to the poor guy. So now the poor guy isn't as poor, right? That's why the plus charge is dispersed. So that's the answer to this question. Okay. So you must tell me that the p orbital of the positively charged carbon, okay, overlaps with the pi electron cloud of the benzene. Once it overlaps, hence, high electrons from benzene can delocalize into the carbon with the positive charge. This will make the carbon not as poor as before, right? That's why the plus charge will be dispersed to a large extent. It will stabilize the carbocation. That's why it favors SN1. So you see how we unpack this question. I work with my way backwards, right? But then your answer is supposed to start from here and then you write all the way until this part. So let's go through this one more time. Okay, it favors SN1. That's what the question is asking. Meaning, it is a very stable carbocation, meaning that the plus charge is very dispersed. How does it become less poor? It's because you have the benzene helping. How come the benzene can help? Because of the fact that the p orbitals overlap, that's why the benzene can help. If there's no p orbital here, the benzene can't help anything. Does that make sense? Okay, so in other words, okay, very important question. You might want to put a star here. Okay, it's a very special scenario. Your school will definitely test in the future. Okay, right? So I must discuss anytime there's anything right beside a benzene, you have to talk about delocalization. Just warning first. Okay, so guys, can you all take a look at part B now? Okay, for part B, let's take a look. They ask for 2-chloroethyl benzene. Just try to draw this structure first. Okay, once you've gotten it, right? Okay, let's try to answer the next part. Okay, so explain why this mechanism is preferred. What mechanism are they referring to here? Okay, SN2. It's the opposite of the first one now. Okay, so the question here, right, it undergoes hydrolysis via a different mechanism. Okay, now I know hydrolysis kind of seems like a very vague term over here. Okay, but first, 2-chloroethyl benzene should look like this, correct? 2-ethyl benzene, 2 carbons, but now it's on the second carbon, correct? Okay, compared to this. Okay, hydrolysis means okay, you can think of it this way first. Okay, hydrolysis here, I know it's about water. Okay, but basically, right, we are just subbing OH minus with the Cl. So this is the nucleophile trying to attack the carbon now. Okay, it's trying to substitute Cl with OH. A little bit different from this. This one was attacked by a Cn minus. Okay, but I know hydrolysis because you're not very used to the term yet. Eventually, you start to see more. Okay, but anyways, why is SN2 preferred? Look at the question now. This question here is asking, why is SN2 preferred? Why? If they now ask us to argue for SN2, what factor do we need to discuss? Steric hindrance. Nothing about stability now, no more already. Okay, but what? Why is SN2 preferred for this guy? Good. In fact, this guy is a primary or secondary or tertiary. What's this? It's primary, right? So already it's really supporting our idea. It's primary, so it has less alkyl groups, bulky groups. So that's why there will be low steric hindrance. That's our answer. Okay, so you just tell me if there are less bulky alkyl groups, or there's only one bulky alkyl group. Okay, bonded to CCl. Okay, hence there is little steric hindrance. Done. Much easier to explain. And since there are less steric hindrance, there's less steric hindrance here. Okay, you just favor SN2. Okay, now they ask us for the products. Okay, let's just very quickly draw the products. Or it should be just product, not products. There's only one product over here. Okay, yeah, lor. So I'm just substituting this CL for OH. That's pretty much it. Yeah. Okay, so this question here introduces the idea of arguments. Okay, how to argue. Okay, all good. Okay, we shall take a 5-minute break first. Okay, then later we shall go through one more final question. Yeah, then we will be done for today. Do you happen to have MacBook charger? No, right? Shit. Okay, continue our last question. I want you all to turn over to question 12. Okay, then after this, we are done with the topic. Okay, so at question 12, I aim to do all 4 parts. Okay, but except for part B, part B, right, I only want to do part 1. So what I want you guys to do, do 12A and B part 1. Just that. Because after B part 1, I'm going to move on to C and D. Okay. What's up? No, curious. In the definition of the nucleophile cannot be found in our notes here because it's taught in intro to organic chem. Okay, so just try the rest first if you don't know what the definition is. Yep, it's just one step. Okay, because this question here is to use to follow on C5. Yes, okay, so let's talk about A and B first. Okay, they want one step here. Okay, so as you can see, there's no increase in number of carbon atoms. So all you need to do here is just undergo a substitution. Okay, remember the conditions here, right? It is your ethanolic concentrated ammonia, and you want to heat it in a sealed tube to prevent the ammonia from escaping. Okay. Okay, so once you've gotten this, then they ask for part C, right? Because they want you to draw a mechanism. Okay, but anyways, I'll go over the definition of a nucleophile also. This is the full definition. Okay, so first of all, you already know that it has to be an electron-rich species. Okay, it's an electron-rich species, and how do you know it is electron-rich? It's because what does it contain that makes it an electron-rich species? Yes, okay, that contains lone pair of electrons. Okay, and these lone pair of electrons are used to attack what? What kind of species does it attack? Okay, electrophiles, or in other words, you can tell me electron deficient species. Okay, or I can just say used to attack electrophiles. Okay, the main idea here is you must at least tell me electron rich and lone pair. These two are minimum requirement. The last part we need to do. Okay. But other than that, okay, you can take a look at B part one. Oh, sorry, B part one is done already. Okay, you take a look at part C. Part C, they want you to draw a mechanism for the formation of this species. Basically, they want you to draw the exact mechanism here. And then once again, you need to identify whether it's SN1 or SN2. Now, if the question never say any clues or like racemic mixture or whatever, right, you should use your own assumptions. Like as we mentioned, usually SN2 is favored by primary, SN1 is favored by tertiary. Okay, so in this case, what is the mechanism for this question? Okay, it should be SN. What, okay, what do you say is SN2? Yes, okay, it's a primary halogenoalkane. That's as SN2 reaction. Okay, so that's the answer for this question. Okay, so we haven't tried drawing an SN2 mechanism yet. Okay, so this is our first time, the last time during the lesson. Okay, so I'm going to give this a try. Okay, after you're done with that, we also need to take a look at part B. SN2 is a little bit more tricky because we need to show the stereochemical formula like this. Okay, remember, I talked about how you should draw the stereochemical formula. Your halogen should be the only one, right, that is horizontal, whereas the others, right, should be leaning towards the left, like this. Okay, and once you draw this already, you fill in all the bonds on this carbon here. So there are two H's, and then there's one CH2. So let me put my H's here. You want to put the CH3 here also can. It doesn't matter where you place them. Just make sure that the bonds are all leaning towards the left, except for the Br. Now, how does the nucleophile attack? Okay, from the back. So here, the nucleophile is, what's the nucleophile used in this question? Ammonia. You take your ammonia NH3 like this, show your lone pair on N attacking the C. The C must have partial charges, and the bond must break for CBr. Okay, those are the arrows again. From here, you can do your slow step and go and draw your transition state. Okay, your transition state is where the ammonia hasn't really formed a bond yet, and the bromine hasn't really formed a bond yet. It's kind of like the Fusan-Fusu stage. Okay, that means you will get this. But remember, I'll take a look at the solid and dash wedge. The solid and dash wedge need to change positions. The solid was on the right, now the solid must be on the left. The dash was on the left, now the dash must be on the right. Okay, then you just fill this in like that. Is there an overall charge on the transition state? No, because left hand side is neutral, right hand side should still be neutral. So you should just write down transition state. Last but not least, we can finally form the bond with NH3. And now everything will lean towards the right hand side, as you can see here. So the solid and dash wedges would have been inverted. This is the inversion of stereochemistry. Okay, and you also have Br minus over here. Am I done with the mechanism? No. Okay, we went through this mechanism exactly in class before. Okay, this N here must have a what? Yes. Okay, it's giving away its electrons, it must gain a positive charge. And all the more, right, you have 4 bonds. 4 bonds over here, right, impossible to stay, right? Okay, your nitrogen is a plus charge here. So how do you get rid of the plus charge? One of the NH bonds needs to break, right? Because N can only hold 3 bonds. So one of the NH bonds need to break, but somebody must steal away the H. Who can do that? Yeah, good. Exactly. Br over here will steal away this H, so it will attack. Then the bond of electrons here must go where? Go to N. Since N is poor, he needs the electrons, give it to him, and that's how you can get your final answer. Okay, where you have NH2. Okay, and then the other product will be HBr. So that's how HBr is formed. Okay, slightly tricky mechanism with a slightly extra step. Any questions so far? Okay, no. Okay, we're going to look at our last question, which is part D, and then we go through this together, and then we're done for today. Okay, these are important questions. That's how I want to do this. Okay, Anna. Hey guys, going to read through part D. I want you guys to just take a look at what's happening here. Okay, they're saying that there's a byproduct. Okay, oddly enough, it's a byproduct during this reaction. Okay, so while in the formation of our product, which is this, at the same time, you get a byproduct that is C8H20 and Br. What the hell is this? How does this product come about? Okay, there's also another very important keyword here. I wanted to highlight immediate precipitate with silver nitrate. It's a very important keyword. Immediate precipitate formed with AgNO3. The keyword here being immediate. Okay, how is a precipitate formed immediately? We kind of did cover this question just now, right? One of the MCQs. Okay, if you can form the precipitate immediately, what does that imply? Okay, you don't need to break any bond, right? Any CCl bond. Okay, so let's write it down again. If you can form immediate precipitate, that means there's no need to create in this case, CPR1. Because there isn't even a CPR1. That means the PR is now existing as a what? It already is a what? It's already an ion. Okay, the PR, I minus ion. It is already part of the compound. Can see that? What kind of byproduct will have a Br minus ion just floating about? A salt, yes. If there's Br minus, that means the rest of the molecule must have what charge? A plus charge. What exactly is this molecule even? How does it have 8 carbons? I started off with only 2 carbons. How does it propel all the way to 8 carbons? Because it's the ammonia salt. The what ammonia salt? The 4 degree, yes. Quaternary ammonium salt. Now remember guys, I told you this, the original compound had 2 carbons and somehow it can propel all the way to 8 carbons. Because there's a pattern over here. First is 2 carbons, does it jump straight to 8 carbons? Next is what? 4, then? Yeah. This is the primary amine, secondary amine, tertiary amine. This is the quaternary ammonium salt. The ammonium salt allows you to have a Br minus. Okay, so that's why this is the salt. So what I want you guys to do, draw CaH20 and Br. Give it a try. Okay, remember, this is the concept of multi-substitution where you have different wings. Right? Okay, how big is each wing? Okay, yeah, that's your answer. Just put them closer together. That's it. Okay, how big is each wing, by the way? We take a look at my jump from 2 to 8. How many carbons is each wing? 2 carbons. That's why it becomes 2, 4, 6, 8. But you're adding 1 wing, 2 at a time, right? Okay, so what's happening over here is I have a 2 wing, 2 wings, 2 wings, 2 wings. The nitrogen must have a what? Positive charge. And then you can just put the Br minus side by side. This whole thing is CaH20 and Br. That's it. Okay, so now I know they asked us to write equations to account for its formation, but I already wrote the equations just now, right? Okay, when we went through the recap. It's the same way as how we form this thing. You can write every single one, but usually, guys, they will only ask you guys to draw the byproduct. Then they won't really ask you guys to write the equation. But more importantly, I want you guys to acknowledge this. Immediate precipitate form means that there is a Br minus free ion. Okay, sometimes they can use the word there's a free Br minus, meaning it is not bonded. Okay, it is not bonded to anything. And because it is not bonded, the only thing that has a free Br minus is this quaternary ammonium salt. So that's how you know, right? It's substituted 4 times. Your tertiary and secondary, right, do not have a free ion. Okay, the bromine is still attached one. The only time where it is free is only here. That's it. Okay? That's pretty much it for today. Okay, any questions? Okay, so we'll start on a more chill topic next week. Okay, we're going to deviate a bit from organic chem. Okay, any more organic stuff, we're going to touch on it next year already. We've covered quite a bit. Okay, so we're going to touch on this topic called periodic table for the last 2 lessons. It's done more chill. It's a lot more like equations and stuff. Yeah, very, very condense heavy. Okay, but other than that, right, okay, they will be done for the year. As for when the consult will be, right, quite likely to do it in between the 19th to 22nd period. We'll just arrange like 1 day in that period. Okay, just come back and go through the paper. Okay, I have the papers and review. Okay, so yeah, that's about it for today.